We've looked at the conservation of energy for a closed system. Now we want to apply that and create the conservation of energy equation for an open system. So let's look at that now. Conservation of energy. Open systems. And so what we're looking at, what we're going to do is apply the first law for closed systems. Q is equal to delta E plus W. And we're going to let delta E be the change of the energy of the control mass is equal to E of the control mass at T plus delta T minus E of the control mass at time T. So just as we did with the conservation of energy, and I'll show you, just as we did with the conservation of energy, we have that, I have Q minus W is equal to delta E. So I'm just rearranging the equation there. And so what happens now is I have this open system. So here's the open system. And again, you can look in the text and go through this in detail. I'm not going through all those steps. And so that's why there are textbooks. And so what we have here, I have mechanical work. So to get work, mechanical work into or out of an open system, I need an impeller. It either has to be a turbine, and so it spins and extracts energy from the fluid, or it's like a pump and it's putting energy into the fluid. The only way it can happen. And now I'm going to have fluid flow through this open system, just as we did with the conservation of mass, and I have a heat source here. So I can have Q. So I can have Q go in also, so I have a heat source. And now what happens in the development is what I'm going to do, as I did before, is I look at the control mass. So I hit it with a strobe light, boop, everything's illuminated, and I apply this equation where delta M is going to be this, because I do blip, blip, and then this moves on to regions 2 and 3. So then I go out to regions 1, 2, and 3. And just as we did with the conservation of mass, we do it for the conservation of energy. And we are going to come up with the following equation. All the details are in the text, and I encourage you to read them if you're so interested. Most students like to read proofs as part of bedtime reading, so it makes sure they fall asleep. But you know, maybe you're the exception. And so now if I look at this, I have that the change of the energy of the control volume dt is equal to Q dot minus W dot plus M dot in E in minus M dot out E out. So this is the general expression, and I can have multiple things going in, I could have multiple things going out, I could have a summation here if I wanted to. And so, but this is a simplified form. So this is unsteady. If I want steady state, then I can get rid of this term, which we'll do in a while. This work term, W dot is equal to W dot mechanical plus W dot flow. So the mechanical work is what I indicated here. Mechanical power is where we have this impeller putting stuff in or out. The flow work is work that was done down here somewhere. So before the fluid got there, I had to put work into the fluid to get it into the control valve. So I had to do something to get it in and something to get it out. So W dot flow is equal to M dot times pressure times specific volume. And this is from outside system. And so now I can rewrite this equation Q dot minus W dot mechanical plus M dot in E plus PV in minus m dot out, E times E plus PBO. And so for steady state, which we get to, so we can simplify this and we'll get to a couple equations that we'll use. So the next few equations are part of the development, then we'll get to the equations that you apply in the first law analysis. So if the change of the energy control volume of time is 0. So this means within the control volume, if I look, so if I have my control volume, stuff's going through it. And so it doesn't mean that there can't be changes of energy across it. It means that when I look this time, whatever property I see here, and I look back again, it's the same thing. That's what steady state means, that it doesn't change with time, even though there can be a change as it goes across the control volume. So then I can have energy in equals energy out. And I have Q dot plus the sum of the m dot in. Now here I'm putting in the summation signs. E plus PV in is equal to W dot mechanical plus the sum of the m dot out. E plus PV. The text doesn't have these summation signs, but sometimes we need them. I mean, it was implied that I could put one over here, but I'm just making it more explicit here. And at some point, we'll drop it because it becomes annoying to write it all the time. And so we looked and we saw that E is equal to U plus KE plus PE. And we have enthalpy, H is equal to U plus PV. So this is specific enthalpy. And large capital H is U plus pressure times volume. So now if I look here, if I look at this, I have U plus PV gives me H, so I can come up with a couple of equations for the first law, one involving H or enthalpy and the other one involving U plus PV. And these are the two equations that you'll be using in your first law analysis. So now let's assume m dot in equals m dot out equals m dot. So very often we have this situation where we have the fluid going in is the same as the fluid going out, and I don't have two things in and one thing out. And so we can write these two equations. So Q dot plus m dot times U plus PV plus KE plus PE in is equal to W dot plus m dot times U plus PV plus KE plus PE out. And, so this is one important one. The second one is I write the same thing with enthalpy. I have m dot times H plus KE plus PE in is equal to W dot plus m dot times H plus KE plus PE out. So what we have, these are the first law for an open system, steady state, and we apply these in different situations. We also, if you look in the text, we developed an expression for the power. And so for the power, we have it's equal to minus m dot times VdP. And so if you'll notice that the minus sign, if dP is increasing, such as I'm putting work in and having it be a pump that increases the pressure, work goes in. So if dP is positive, I want it to be a minus because I'm putting it into the system. for a turbine where dP is negative and expanding, this will be a minus sign times a minus will give me a plus. And so thermodynamically, this equation works. So we have these equations for open systems. For a closed system, I have Q is equal to delta E plus W, and W is equal to the integral of PdV. So the parallelism is I have this for open and this for closed. Now let's look at an example for open systems. So this will be problem 323. So again, I urge you to go to the textbook and look up problem 323. This is a problem that people had difficulty with, so I thought it'd be worth pursuing here and how we figure out what to do. So we have a furnace. So in this case, there's a furnace and we're heating a house. And so what it is we have the furnace. And the furnace receives air and fuel. And you're told that the air has an enthalpy, H is equal to 302 kilojoules per kilogram. And this is the air, and the fuel, H sub F, has an enthalpy of 43,027 kilojoules per kilogram. We have combustion occur, and the gases, Hg, is equal to 616 kilojoules per kilogram. And since it's a furnace, we have heat leaving, Q dot's leaving, and what you're told is that the house, here's the house, it needs 17.6 kilowatts. So it needs this amount of heat to keep the house warm. So to keep the house warm, that has to go into the house, has to leave the furnace and go into the house. And so the heat's leaving the furnace. This is our open system. That's the open system. The house has nothing to do with the open system. The house sets the context. This is the open system. And we were also told that there were 17 kilograms of air used for each kilogram of fuel. And this is the air-fuel ratio. So this is RAF, but it's the air-fuel ratio. And so now what we've done is you've read the problem, so you went in and read the problem. I translated it into a sketch. So I have a sketch, system is open. So it's an open system. Process, it didn't say, but it's P equals C. And energy, yes. So automatically we do the first law. So it's like, I don't know what to do, wrong. You know what to do, first law. Since we're given enthalpies, we will use the first law equation with enthalpies. So I have Q dot plus N dot air times H plus KE plus PE of the air plus N dot fuel times H plus KE plus PE of the fuel is equal to W dot plus M dot of the gas times H plus KE plus PE of the gas. So I did the first law equation, and now we get rid of the terms that don't apply. There's no change of kinetic energy, no change of potential energy. And what about the work? So what about the work? Is there an impeller going into or out of the furnace? No. So you have to think about what's happening. There's no impeller. The only way to get work in or out of an open system is with an impeller. There's no impeller, no work is done. And what about, where did this mass of the gas come from? Where did that come from? Well, I have m dot A coming in here, and I have m dot F coming in here. They mixed it, nothing disappeared, it didn't go anywhere, so they both combined and became this. So I know that m dot J is m dot A plus m dot F. So this problem has the conservation of mass associated with it, first law, and paying attention to what's happening so we get rid of the work term, which is not there. So now I have that Q dot plus m dot A HA plus m dot F HF is equal to m dot A plus m dot F HG. So what I know is this, so I know this. So I have minus 17.6 kilowatts. So it's leaving, hence it's minus, plus m dot A times 302 plus m dot F times 43027 is equal to m dot A plus m dot F times 616. Oh dear, I have one equation and two unknowns. What are we going to do? So from an algebraic problem-solving perspective, you look to see if there's any other information given. The other piece of information is this. How do I use it? What does that mean? So I know that 17 is equal to MA over MF. Kilograms of air per kilogram of fuel. It's also equal to m dot A over m dot F. The seconds on both the top and the bottom cancel out, so it's the same. So what could I do? I could divide through this equation by n dot F and come up, and then I should have only one unknown. So let's do that. I have 17.6 over m dot F. A lot of times students don't divide every term by m dot F, so they leave the m dot F off this term, plus m dot A over m dot F times 302 plus 1 times 43027 is equal to m dot A over m dot F plus 1 times 616. And if I substitute in here 17 and 17 and solve for this, I get that m dot F is equal to 0.30 4747 kilograms per second. That isn't what the problem asked for, however. They want to know how many kilograms per day you used. So I have to multiply by 3,600 seconds per hour and 24 hours per day. And this turns out to be 41 kilograms per day. And so now, so that I'm not the only one doing home problems, for homework, do 311, 321, 327, 348, 350. And now what I'd like to do is look at another type of open system, a heat exchanger, which we do a lot of. So throughout the course, heat exchangers are one of the elements of a thermal system that we look at. And in chapter 3, it didn't go through a heat exchanger, so I thought I would, excuse me, go through it now. And so let's look at a heat exchanger, and if I take a diagram, basically what happens is I'll have a tube, I have tubes, and so there'll be a bunch of tubes. So I'm going to have something, I'll have cooling water go through the tubes, cooling medium. So it'll go through the tubes, and I'll have steam come in and steam come in and go over the tubes. So I could have steam come in, and then I'd have a condensate come out. So the steam comes in and condenses as it flows over the tubes. The water goes through the tubes and increases in temperature. So that's what's going on. So if I have steam, and here I'll have 5 kilograms per second, and it will have an enthalpy of 2570 kilojoules per kilogram. And it'll exit with an enthalpy of 160.5 kilojoules per kilogram. And I'll call this state 1 and state 2. And then for the cooling water, it'll go in at state 3 and leave at state 4. At state 3, H is 104.4 kilojoules per kilogram. And at state 3, really. And at state 4, H is equal to 167.3 kilojoules per kilogram. And so very often in the course, what I'll do is I'll draw something like this, and I'll have this be the cooling water, and this be the steam. So I don't go through drawing tubes and imagining that happens. It's like the cooling water goes through tubes, steam goes over the tubes and condenses. So this becomes a more schematic way of representing this.